What if I told you that right now, as you listen to this, an object from another star system is doing something that violates everything we thought we knew about how the universe works? Something is pushing material forward, ahead of its own trajectory, directly into the solar wind, and nobody, not NASA, not the European Space Agency, not a single physicist on this planet, can explain how that is physically possible. On November 22nd, 2025, an amateur astronomer in Puerto Rico pointed his telescope at the sky and captured 3 images that sent shockwaves through the scientific community. What he photographed was not a comet behaving like a comet. It was something else entirely. A structure extending forward, toward the sun, clearing a path through space like nothing we have ever documented in the history of astronomical observation. By the end of this video, you will understand why some of the brightest minds in astrophysics are now openly questioning whether 3I Atlas is a natural object at all, and what the next 25 days could reveal as it makes its closest approach to Earth. Before we begin, always remember to like this video. It tells your algorithm that you love these topics and that you want more of them. And if you enjoy our calming science documentaries, do not forget to subscribe and hit that notification bell so you never miss an update. Now tell me in the comments, where are you listening from tonight? What time is it there? And here is my question for you. Do you believe 3I Atlas is a natural comet, or something else entirely? I am always curious to hear your thoughts. Now let us dive deep into what might be the most significant astronomical mystery of our lifetime. The forward-advancing anti-tail that defies every law of physics. To understand why the scientific community is so disturbed by what we are observing, you first need to grasp a fundamental principle that has governed our understanding of comets for centuries. When a comet approaches the sun, it heats up. The frozen volatiles on its surface, the ices and compounds that have been locked in deep freeze for billions of years, begin to sublimate. They transform directly from solid to gas, and as they do, they create what we call a coma, that beautiful glowing halo you see surrounding the nucleus in photographs. But here is where it gets interesting. The sun does not just warm these objects, it actively pushes against them. Solar radiation pressure and the solar wind, that constant stream of charged particles flowing outward from our star at hundreds of kilometers per second, these forces act on all that liberated gas and dust. They push it backward, away from the sun. This is why comet tails always point away from the sun, regardless of which direction the comet itself is travelling. It is not the comet leaving a trail behind it like a car on a dusty road. It is the sun actively blowing that material in the opposite direction. This has been observed in thousands upon thousands of comets. It is one of the most reliable, predictable behaviours in all of astronomy. Until now. 3I Atlas is doing something that should be impossible. It is projecting material forward, ahead of itself in the direction of its motion through space. Not behind it where the solar wind should push it. Not perpendicular to its path where we might expect some unusual outgassing. Forward, toward the sun, against the solar wind. Think about that for a moment. Imagine you are standing in a hurricane, facing directly into the wind. Now try to blow a handful of sand forward, into that wind. You cannot do it. The force pushing against you is simply too strong. Yet 3I Atlas is somehow accomplishing exactly this on a cosmic scale, extending material millions of kilometers ahead of its trajectory, as if the solar wind simply does not apply to it. When the Hubble Space Telescope first captured images of 3I Atlas back in July of 2025, astronomers noticed something peculiar. There was an extension of material pointing toward the sun. At first, many assumed this was a perspective effect, what we call an anti-tail. Sometimes, when we view a comet from certain angles, the geometry of its dust trail can create an optical illusion that makes it appear as though material is extending sunward when it really is not. This happens when we are looking edge-on at a sheet of dust particles spread along the comet's orbital plane. It is a well-understood phenomenon. But as weeks passed and observations continued, it became increasingly clear that what we were seeing was not an optical illusion at all. On October 2nd, 2025, NASA's Mars Reconnaissance Orbiter turned its high-resolution camera toward 3I Atlas as it passed within 29 million kilometers of the red planet. The high-res camera, one of the most powerful imaging instruments we have ever sent to another world, captured something that changed everything. The image showed 3I Atlas with a glowing extension advancing ahead of it in the direction of its motion. Not pointed at the sun necessarily, but forward, clearing a path through space. The extension created an X-shaped pattern around the nucleus, with material projecting both ahead and behind the object. Dr. Avi Loeb of Harvard University was among the first to recognize the profound implications. He wrote that it is easy to explain a plume of gas and dust extended toward the sun as a result of illumination of pockets of ice by sunlight, or away from the sun as a result of radiation pressure or the solar wind. It is also possible to explain a trailing stream that the object leaves behind, as drag from the solar wind slows material down relative to the object. But it's much more difficult to account for a plume extended perpendicular to the direction of the sun and ahead of the object. The scale of what we are observing is staggering. The extension in the high-rise image spans approximately 3,000 kilometers. At the typical thermal speed of volatiles that sublimate from the surface of a natural comet, it would take about a day to cross that distance. But the phenomenon has persisted for months now, growing more pronounced rather than dissipating. By early November, as 3I Atlas emerged from behind the sun following its closest approach, on October the 29th, new images revealed the anti-tail had not disappeared. It had intensified. On November the 8th, 2025, astronomers Michael Yeager, Gerald Riemann, and Enrico Prosperi captured deep images showing a complex tail structure, unlike anything documented before. 4 to 5 distinct jets or tails were fanning out in multiple directions from the nucleus. Some observers noted the structure resembled Comet C 2016 R2, an unusual long-period comet extremely rich in carbon monoxide and nitrogen, but poor in dust. But even that comparison falls short of explaining what 3I Atlas is doing. Then came November 22nd. Amateur astronomer Efrain Morales Rivera pointed his 305mm telescope at the pre-dawn sky from Aguadilla, Puerto Rico, and captured 3 images that have sent the astronomical community into overdrive. At low resolution, 3I Atlas appeared as an unremarkable green comet without a visible tail. But when the image brightness was enhanced and processed, the truth emerged. Bilateral gas emissions extending from a compact central core, a prominent forward-facing anti-tail stretching toward the sun, and perhaps most disturbing of all, the complete absence of the expected dust trail that should stream behind any comet after its closest approach to the sun. Let me be absolutely clear about what this means. Standard cometary physics predicts that an object losing more than 13% of its mass during perihelion passage, which 3I Atlas has according to NASA's own data, on its non-gravitational acceleration, should produce a massive, visually prominent tail of dust and ionized gas being pushed away from the sun. The expected tail length for an object at 3I Atlas's current distance and mass loss rate would extend hundreds of thousands of kilometers. Instead, we see material advancing forward, ahead of the object, where no natural process should be able to put it. Dr. Loeb has proposed a hypothesis that would have seemed outlandish just a few years ago, but now demands serious consideration. What if this forward extension is not a natural phenomenon at all? What if it is a technological signature, a beam of light or particles being used to clear hazardous micrometeorites from the flight path of whatever 3I Atlas actually is? Think about that. If you were sending a craft across interstellar space, a journey of billions of years through the cosmic shooting gallery of dust, ice and debris that fills the void between stars, you would need some way to protect your vessel. Even microscopic particles become deadly projectiles at the velocities involved in interstellar travel. A forward-facing shield or deflection system would not be optional. It would be essential for survival. But there is another possibility, perhaps even more intriguing. What if 3I Atlas is not just protecting itself, but actively harvesting material as it travels? The solar system is filled with metallic fragments, dust particles rich in iron, nickel, and other useful elements. If 3I Atlas were deploying some form of collection system, perhaps using nanotechnology to gather resources ahead of its path, that would explain both the forward extension and another anomaly that has baffled scientists: the unusually high concentration of nickel in its gas plume. Spectroscopic analysis has revealed that 3I Atlas contains far more nickel than iron in its emissions, a ratio that resembles industrially produced nickel alloys far more than any natural comet we have ever studied. What if the nickel we are detecting is a byproduct, the waste product of some kind of manufacturing or refinement process happening within the object itself. In situ resource utilization, gathering raw materials from the environment and processing them during transit, is exactly the strategy we ourselves plan to use as we colonize the solar system. Why would we assume an interstellar traveller billions of years more advanced would do anything different? The mainstream scientific community, predictably, is not yet ready to embrace these interpretations. NASA officials have repeatedly insisted that 3I Atlas looks and behaves like a comet, that all evidence points to it being a natural object. And to be fair, there are natural explanations that have been proposed. Perhaps the forward extension is caused by extremely large dust grains that are less affected by solar radiation pressure. Perhaps unusual outgassing from vents on the sun-facing side of the nucleus is producing directional jets. Perhaps the carbon dioxide-dominated composition of 3I Atlas, with its 8-to-1 ratio of carbon dioxide to water, creates behaviours we simply have not observed before because we have never encountered an object quite like this. But here is what troubles me about those explanations. Every time we propose a natural mechanism for one anomaly, another anomaly appears that the explanation cannot account for. The forward anti-tail, the missing dust tail after perihelion, the nickel-to-iron ratio, the X-shaped pattern in the high-rise images, the collimated jets that should be smeared by the object's rotation, but somehow remain tightly focused. Each of these, individually, might be explained away. Together, they form a pattern that demands we consider possibilities beyond the comfortable assumption that we already understand what we are looking at. And now, as 3I Atlas continues its journey outward from the Sun, new evidence has emerged that pushes the mystery even further into uncharted territory. On November 20th, 2025, a stacked image composed of 20 exposures revealed something that no one was expecting to see. Two narrow lines extending sideways from the nucleus, perpendicular to both the tail and the antitail, creating an X pattern that cannot be explained by any known cometary process. Some researchers believe these might be satellite streaks, artifacts from objects passing through the field of view during the long exposure, but others are not so sure. If those lines are real, if they represent material or objects extending outward from 3I Atlas in directions that make no physical sense for a natural comet, then we may be witnessing something far more significant than debris from an icy rock. We may be watching something deploy. A 1 in 26,000, the Jupiter Hill radius, precision, that NASA cannot explain. There is a number that has been keeping astrophysicists awake at night, a calculation so improbable, so statistically unlikely, that it challenges everything we thought we understood about random chance in the cosmos. That number is 1 in 26,000, and it represents the odds that 3I Atlas, an object supposedly drifting randomly through the galaxy for billions of years, just happened to adjust its trajectory to arrive at precisely the most useful location in the entire Jovian system. Not close to Jupiter, not in the general neighbourhood, but exactly at the boundary where Jupiter's gravity can capture objects and hold them in stable orbit. The margin of error is less than 1/10 of 1%, and as you are about to discover, this precision was enabled by a mysterious course correction that occurred while 3I Atlas was hidden behind the Sun, invisible to every telescope on Earth. To understand why this discovery has sent shockwaves through the astronomical community, you first need to understand a concept called the Hill radius. Every massive object in the solar system, every planet, every moon, exists within the gravitational influence of the Sun. The Sun's gravity is what keeps the planets in their orbits, what prevents them from drifting off into interstellar space. But within certain distances of each planet there exists a region where the planet's gravity temporarily wins out over the Sun's pull. This region is called the Hill sphere, and its outer boundary is the Hill radius. Think of it as a planet's personal gravitational bubble. Inside this bubble, an object can be captured. It can be placed into orbit around the planet without the Sun pulling it away. Outside this bubble, the Sun's gravity dominates, and any object will continue on its trajectory around our star rather than becoming bound to the planet. For Jupiter, the largest planet in our solar system, the Hill radius is approximately 53.5 million kilometres. This is a staggering distance, reflecting Jupiter's enormous mass. But in the context of the solar system's vast scales, it is a remarkably small target. Jupiter orbits the Sun at an average distance of about 780 million kilometres. Its Hill sphere represents less than 7% of that orbital radius. For a randomly arriving interstellar object to pass through this precise zone by chance alone is extraordinarily unlikely. Now here is where the story becomes genuinely unsettling. 3I Atlas is scheduled to make its closest approach to Jupiter on March 16th, 2026. Using the most precise trajectory data available from NASA's Jet Propulsion Laboratory, researchers have calculated that the object will pass within 53.445 million kilometres of Jupiter, plus or minus approximately 60,000 kilometres of uncertainty. Compare that to Jupiter's Hill radius of 53.502 million kilometres. The match is almost perfect. 3I Atlas will graze the very edge of Jupiter's gravitational sphere of influence, arriving at the precise distance where objects can be captured into stable orbits with minimal energy requirements. Dr. Avi Loeb was among the first to recognise the profound implications of this orbital geometry. In his analysis, he calculated the statistical probability of this coincidence. A margin of 60,000 kilometres out of 53.5 million kilometres corresponds to a precision of roughly 1 part in 1,000. But when you consider the full diameter of Jupiter's orbit around the Sun, the probability drops to approximately 1 in 26,000. For context, you're more likely to be struck by lightning in your lifetime than to witness an interstellar object randomly achieving this level of orbital precision. But the story does not end with mere improbability. What makes this discovery truly extraordinary is how 3I Atlas achieved this trajectory. The object did not arrive in our solar system already aimed at Jupiter's Hill radius. Something changed its course along the way, and that change happened at the most strategically opportune moment possible. When 3I Atlas reached perihelion, its closest approach to the Sun on October 29, 2025, NASA detected something unexpected in its orbital data. The object exhibited what scientists call non-gravitational acceleration. This is a fancy way of saying that 3I Atlas was not moving exactly as gravity alone would predict. Something was pushing it, altering its trajectory by a small but measurable amount. The acceleration was measured at approximately 5 times 10 to the negative 7th power astronomical units per day squared. In everyday terms, this is an incredibly tiny push. But over the weeks and months of 3I Atlas's journey, this small acceleration accumulated into a significant change in its path. Here is the critical detail that has researchers so disturbed. The magnitude of this non-gravitational acceleration is precisely what was needed to shift 3I Atlas from a trajectory that would have missed Jupiter's Hill radius to one that will graze its edge with surgical precision. According to Dr. Loeb's calculations, the acceleration introduced a course correction of approximately 100,000 kilometres. Without this adjustment, 3I Atlas would have passed outside the Hill sphere. With it, the object will arrive at the perfect distance to deploy probes, satellites, or other technological devices that could become permanently captured in Jupiter's gravitational influence. The timing of this manoeuvre is equally suspicious. 3I Atlas reached perihelion while it was hidden behind the Sun from the perspective of Earth-based observatories. For several weeks surrounding its closest solar approach, no telescope on our planet could observe what the object was doing. It emerged from behind the Sun in early November, already on its new trajectory, already aimed with impossible precision at Jupiter's gravitational boundary. We do not know what happened during those hidden weeks. We cannot know because we were physically unable to watch. In astronautics, there is a principle called the Oberth effect that makes this timing even more significant. When a spacecraft wants to change its trajectory most efficiently, the optimal moment to fire its engines is at the point of maximum velocity, which for any object in a solar orbit means at perihelion, at closest approach to the Sun. An impulse delivered at perihelion produces a much larger change in the final trajectory than the same impulse delivered at any other point. This is basic orbital mechanics, understood by every space agency on Earth. If 3I Atlas were a technological craft executing a planned maneuver, perihelion is exactly when you would expect it to act. Consider what this orbital geometry would mean if 3I Atlas is indeed artificial. Jupiter's Hill radius is not just the boundary of gravitational capture. It is also the location of the Lagrange points, specifically L1 and L2, where the gravitational forces of Jupiter and the Sun balance each other out. These Lagrange points are what space agencies call parking orbits. Objects placed at these locations require minimal fuel to maintain their position. They can loiter indefinitely, watching, waiting, without expending significant energy on orbital corrections. We ourselves use Lagrange points for exactly this purpose. The James Webb Space Telescope orbits at the Earth-Sun L2 point. NASA's recently launched ESCAPADE mission will park at a Lagrange point before proceeding to Mars. These locations are the natural staging areas for any sophisticated space operation. If 3I ATLAS were to deposit technological devices at Jupiter's Lagrange points, as it passes through the Hill radius, those devices would need to decelerate from the object's high relative velocity to become captured. At the moment of closest approach, 3I ATLAS will be travelling at approximately 65.9 kilometers per second relative to Jupiter. Any probe or satellite released at that moment would need to shed most of that velocity to enter a stable orbit. The escape velocity from Jupiter's gravitational well at the Hill radius is only about 2.2 kilometers per second. This is a significant energy requirement, but not an insurmountable one for advanced propulsion technology. Dr. Loeb has speculated that if we observe new objects appearing in Jupiter's orbital environment after 3I ATLAS passes, objects we did not put there, it would represent compelling evidence that the interstellar visitor delivered technological cargo. NASA's Juno spacecraft, currently orbiting Jupiter, would be ideally positioned to detect such objects. Future missions could investigate them directly. But the window for observation is limited. By the time 3I ATLAS reaches Jupiter in March 2026, it will be travelling outbound from the Sun, its mission in our solar system, whatever that mission might be, potentially complete. There is another dimension to this discovery that deserves consideration. Why Jupiter? Of all the possible targets in our solar system, why would an interstellar probe prioritise the largest planet? One possibility relates to what Jupiter represents from an astronomical perspective. Jupiter is visible, not just visible from Earth, but visible from anywhere in the galaxy. Its size, its brightness, its distinctive banded atmosphere, these features would be apparent to any civilization with telescopes pointed in our direction. When 3I ATLAS was launched, potentially billions of years ago from a star system we have not yet identified, Jupiter would have been one of the most obvious landmarks in our solar system. The inner planets, Earth and Venus, and Mars, are tiny by comparison. They would have been nearly invisible from interstellar distances, but Jupiter, massive Jupiter, would have stood out like a beacon. If the civilization that created 3I ATLAS, assuming for a moment that it is artificial, wanted to establish a presence in our solar system, Jupiter would be the logical choice. It offers gravitational resources for capturing objects into stable orbits. It possesses a system of moons that could serve as bases or resource extraction sites. It sits at a safe distance from the Sun, beyond the danger zone of solar flares and coronal mass ejections that could damage sensitive technology. And perhaps most importantly, anything placed in Jupiter's orbit would have an unobstructed view of the inner solar system, including Earth. Some researchers have proposed an even more intriguing possibility. What if 3I ATLAS is not just observing us, but protecting us? Jupiter has long been called the solar system's vacuum cleaner. Its massive gravity attracts and captures asteroids and comets that might otherwise threaten the inner planets. A strategically placed detection and deflection system at Jupiter's Lagrange points could spot dangerous objects when they are still far from the Sun, travelling slowly enough to be redirected with minimal force. Such a system would be far more effective than anything we could build on Earth. It would see threats coming years or decades before they reached us. Is this what 3I ATLAS intends to deliver? A guardian system placed by a civilization that visited our solar system long before humanity existed. It would explain the precision of the trajectory, the timing of the maneuver, the targeting of Jupiter's Hill radius. It would also raise profound questions about who sent it, why they care about our survival, and what else they might have planned. For now, these remain speculations. The scientific evidence is limited to orbital calculations and statistical improbabilities. But those improbabilities are mounting. When you multiply the probability of arriving at Jupiter's Hill radius by chance by the probability of the trajectory alignment with the ecliptic plane, by the probability of the anomalous mass and velocity compared to other interstellar objects. By the probability of the unusual chemical composition, the cumulative odds drop to less than 1 in 10 quadrillion. At some point, coincidence stops being a sufficient explanation. And we are approaching that point rapidly. In less than 4 months, 3I Atlas will reach Jupiter. Whatever happens then, whether it passes silently through the Hill radius and continues into interstellar space, or whether it leaves something behind, will determine whether we have witnessed a remarkable astronomical coincidence, or the most significant event in human history. NASA finally speaks, but what they left out changes everything. On November 19th, 2025, after weeks of silence that fueled conspiracy theories across the internet, NASA finally held a press conference about 3I Atlas. The agency released a cache of previously unseen images collected by spacecraft scattered across the solar system. Officials stood before cameras and delivered their verdict with absolute certainty. 3I Atlas, they declared, is a comet. It looks like a comet. It behaves like a comet. All evidence points to it being a natural object from another star system. Case closed. Nothing to see here. But as the astronomical community began analysing those newly released images, it became increasingly clear that what NASA said and what NASA showed were two very different things. And what they left unsaid might be the most important part of the story. The timing of NASA's silence had not gone unnoticed. From October 1st through November 12th, the United States government was in shutdown. Federal agencies, including NASA, operated on skeleton crews with restricted communications. This shutdown happened to coincide almost perfectly with the war 3I Atlas's perihelion passage and the period when it was hidden behind the Sun from Earth-based observation. For 42 days, as the most mysterious object ever to enter our solar system executed whatever manoeuvres it executed at closest solar approach, the world's premier space agency was essentially muzzled. Conspiracy theorists had a field day. Social media exploded with speculation about cover-ups, classified observations, and government knowledge of extraterrestrial activity. When NASA finally broke its silence, the tone was almost dismissive. Associate Administrator Amit Kshatriya stood before reporters and addressed the alien rumours directly. 3I Atlas is a comet, he said. There is no threat to Earth. The agency's official statements emphasised reassurance over scientific detail. They showed images. They pointed to the fuzzy white ball of the coma. They explained that the object was shedding dust and ice as it approached the Sun. They declared the mystery solved, but look more closely at what NASA actually released, and a different picture emerges. The images came from an impressive array of spacecraft. The Mars Reconnaissance Orbiter had captured 3I Atlas during its closest approach to the red planet. The Perseverance rover, exploring Jezero crater on Mars, photographed the interstellar visitor from the Martian surface. The Punch mission, designed to study the solar wind, tracked the object as it passed behind the Sun. The Psyche spacecraft, on its way to a metal-rich asteroid, caught glimpses during September. The Lucy mission, heading toward the Trojan asteroids, added its observations to the collection. Even the venerable Stereo and SOHO sun monitoring spacecraft contributed footage. It was an unprecedented observational campaign, exactly what you would expect for only the third interstellar object ever detected. But here is what troubled careful observers. Despite this wealth of data, NASA's analysis remained remarkably superficial. The agency confirmed that 3I Atlas has a coma, that it is shedding material as comets do, that its trajectory matches predictions for an object influenced primarily by gravity. These are the most basic observations possible. They tell us almost nothing about the profound anomalies that researchers like Dr. Avi Loeb have been documenting for months. Consider what NASA did not address. They did not explain the forward-advancing anti-tail that has persisted since July. They did not comment on why 3I Atlas lacks the expected dust tail after losing more than 13% of its mass at perihelion. They did not discuss the unusual nickel-to-iron ratio in its emissions, orders of magnitude higher than any known comet. They did not acknowledge the X-shaped pattern in the high-rise images, or the collimated jets that refused to smear despite the object's rotation. They did not mention the trajectory precision that will bring 3I Atlas to within 60,000 kilometers of Jupiter's Hill radius, a statistical improbability of 1 in 26,000. Instead, NASA focused relentlessly on what 3I ATLAS has in common with normal comets, while ignoring everything that makes it unprecedented. This selective presentation raises uncomfortable questions. Is the agency genuinely unaware of these anomalies? That seems unlikely given the caliber of scientists involved. Are they still analysing the data and withholding conclusions until peer review is complete? Possible, but the definitive tone of their public statements suggests otherwise. Or is there something about 3I ATLAS that officials have decided the public should not yet know? The most revealing moment of the press conference came when officials discussed the James Webb Space Telescope observations. Webb had studied 3I ATLAS in early August, using its near-infrared spectrograph to analyse the chemical composition of the comet's coma. The results, NASA confirmed, showed an object dominated by carbon dioxide emissions. The agency presented this as evidence of 3I ATLAS's cometary nature. What they glossed over was the extraordinary ratio involved. 3I ATLAS has a carbon dioxide to water ratio of approximately 8:1. This is among the highest ever recorded for any comet, natural or otherwise. Typical solar system comets are dominated by water ice. Carbon dioxide is present but secondary. 3I ATLAS inverts this relationship completely. Why does this matter? Because the ratio tells us something profound about where this object came from and what conditions it experienced. In our solar system, comets form in regions where water ice is the dominant volatile. Carbon dioxide freezes at lower temperatures and requires specific conditions to become the primary component. An 8:1 carbon dioxide to water ratio suggests that 3I ATLAS formed in an environment radically different from anything in our cosmic neighbourhood, or alternatively, that something has fundamentally altered its composition during its billions of years of interstellar travel. Recent research from the Royal Belgian Institute for Space Aeronomy, published just weeks before NASA's press conference, offers one explanation. The study suggests that 3I ATLAS has been bombarded by galactic cosmic rays throughout its journey, potentially for 7 billion years or more. This radiation has transformed the outer layers of the object, creating an irradiated crust that no longer resembles the pristine material it started with. The extreme carbon dioxide enrichment may be a product of this cosmic ray processing, rather than a reflection of original composition. But this explanation, while scientifically elegant, raises its own troubling questions. If 3I ATLAS has been so thoroughly transformed by radiation that its surface chemistry is completely altered, how can we make any definitive claims about its nature? The object we are observing is not the object that left its home star system billions of years ago. It is something new, something created by eons of cosmic bombardment. Making confident statements about what it is or is not seems premature at best. NASA's reluctance to engage with these complexities is perhaps understandable from a public relations perspective. The agency exists in a political environment where funding depends on public support and congressional approval. Appearing to take seriously the possibility that 3I ATLAS might be artificial, even as a hypothesis worth investigating, could invite ridicule and jeopardize resources for legitimate scientific missions. Better to declare it a comet, close the book, and move on to safer topics. But science does not work that way. Science progresses by engaging with anomalies, not dismissing them. The history of discovery is filled with objects and phenomena that were initially explained away as mundane before being recognized as revolutionary. Pulsars were almost classified as instrument noise before being understood as rapidly rotating neutron stars. The cosmic microwave background was initially mistaken for pigeon droppings on a radio antenna. Wegener's theory of continental drift was rejected for decades before plate tectonics became accepted science. In each case, the breakthrough came when researchers took seriously what existing frameworks could not explain. 3I ATLAS presents exactly this kind of challenge. Its anomalies do not fit comfortably within our current understanding of cometary behaviour. The forward anti-tail, the missing dust tail, the industrial chemical signatures, the trajectory precision, the jets that defy rotation, these are not minor discrepancies. They are fundamental departures from what we expect natural comets to do. Addressing them honestly would require admitting that our models might be incomplete, that we might be encountering something genuinely new. To be fair, some of NASA's data did advance our understanding. The Psyche spacecraft observations from September revealed details about 3I ATLAS's trajectory refinement. The Mars orbiter images provided constraints on nucleus size and coma structure. The Webb spectroscopy confirmed the unusual chemical composition that had been suspected since summer, but in each case the implications of these observations were downplayed or ignored in official communications. Perhaps most frustrating is what we still do not know, because NASA has not released the full dataset. The agency has confirmed that spectroscopic observations exist that could reveal the velocity and composition of 3I Atlas's jets. This data is critical because it would allow us to determine whether the jets are consistent with passive sublimation of ice, which would support the natural comet hypothesis, or whether they exhibit characteristics more consistent with directed propulsion. A natural comet's outgassing should produce material moving at hundreds of meters per second at most, limited by the thermal energy available from solar heating. Technological thrusters could produce exhaust velocities of kilometers or even tens of kilometers per second. Dr. Loeb has been calling for exactly this kind of spectroscopic analysis for months. In interview after interview, he has emphasized that the composition and velocity of the jets would be decisive. If the jets are water vapor and carbon dioxide moving at thermally limited speeds, 3I Atlas is almost certainly a natural comet, however unusual. If the jets contain unexpected materials or move at velocities that require powered propulsion, we would need to seriously reconsider what we're dealing with. NASA has the data that could answer this question. As of now, they have not released it. The December 19th closest approach to Earth will provide the best opportunity for ground-based observatories to study 3I Atlas in detail. The object will be approximately 269 million kilometers from our planet, close enough for major telescopes like Keck, the Very Large Telescope, and Gemini to obtain high-resolution spectra. Independent researchers will finally have access to data that NASA cannot filter or selectively present. Whatever the truth about 3I Atlas, it will be harder to obscure when the entire astronomical community can see for themselves. Until then, we are left with questions that official statements have failed to answer. What happened during those hidden weeks behind the Sun? What caused the trajectory adjustment that aligned 3I Atlas so precisely with Jupiter's Hill radius? Why does the object lack the expected dust tail after perihelion? Why do the jets remain collimated despite rotation? Why is the chemical composition so different from every other comet we have studied? NASA says 3I Atlas is a comet. The data suggests it is something we have never seen before. Both statements might be true, but only one acknowledges the profound mystery we are witnessing, and only one opens the door to discoveries that could change everything we think we know about our place in the universe. The X-shaped pattern, and November the 20th. Evidence of smaller objects being released. Something happened on November 20th that the mainstream astronomical community is struggling to explain. A team of dedicated observers, Michael Jager, Gerald Riemann, and Enrico Prosperi, captured a stacked image of 3I Atlas composed of 20 separate exposures, each lasting 100 seconds. What they recorded defies conventional understanding of cometary behavior. Two narrow lines extend sideways from the nucleus, perpendicular to both the tail and the antitail, creating a distinct X pattern that has no business being there according to everything we know about how comets work. These are not artifacts. They are not processing errors. They are real features extending millions of kilometers into space, and they may represent the most significant discovery yet about the true nature of 3I Atlas. To understand why these sideways extensions are so anomalous, you need to think about the forces acting on material around a comet. When a comet approaches the Sun, it sheds gas and dust through sublimation. This material does not simply drift away in random directions. It is immediately acted upon by two dominant forces. Solar radiation pressure pushes particles away from the Sun. The solar wind, that constant stream of charged particles flowing outward from our star, pushes ionized gas in the same direction. These forces create the familiar geometry of cometary tails, always pointing away from the Sun regardless of which direction the comet itself is travelling. Material can also be pushed toward the Sun under certain circumstances. If pockets of ice on the Sun-facing side of the nucleus sublimate with enough force, they can create jets that temporarily resist the solar wind. This is one explanation for the antitail phenomenon, though as we discussed earlier, the antitail of 3I Atlas persists in ways that challenge even this interpretation. But material extending sideways, perpendicular to the Sun-comet axis, that should not happen at all. There is no force pushing particles in that direction. The The solar wind does not blow sideways. Radiation pressure does not push perpendicular to the light source. Gravity does not pull material into these geometries. The November 20th image shows the displayed field spanning approximately 16.7 arc minutes on a side, which corresponds to about 1.6 million kilometers at the distance of 3I Atlas. The sideways extensions are clearly visible, narrow and straight, creating their X pattern with remarkable geometric precision. The sun's direction in the image is toward the lower left, which means the anti-tail points upper right and the normal tail points lower left, as expected. But the sideways jets point in directions that have nothing to do with solar geometry. Dr. Avi Loeb was quick to analyse the implications. In his assessment, there are only two possible explanations for what we are seeing. The first is that the sideways lines are satellite streaks, artifacts from objects passing through the telescope's field of view during the long exposure. Satellites in low Earth orbit frequently create linear streaks in astronomical images, and they can sometimes appear at unexpected angles depending on their orbital inclination. This would be the mundane explanation, and careful follow-up observations could confirm or rule it out. But the second explanation is far more intriguing. If the sideways jets are real, if they actually represent material extending from 3I Atlas perpendicular to the Sun-comet axis, then we may be witnessing the release of smaller objects from the main body. Think about what this would mean. If 3I Atlas is a technological craft, a mothership of some kind, this could be evidence of it deploying probes or mini-satellites during its passage through our solar system. The geometry is actually consistent with this interpretation. If small objects were released from 3I Atlas near perihelion, when the object was at closest approach to the Sun on October 29th, they would have had approximately 22 days to drift apart from the main body before the November 20th observation. At the observed distance of about 1 million kilometers, this implies a relative velocity of roughly 500 meters per second. This is a very reasonable exhaust velocity for chemical propulsion systems. It is exactly the kind of delta-v kick that a spacecraft would apply to deploy a probe on an independent trajectory. But here is what makes this observation even more significant. The X-shaped pattern in the November 20th image is not unprecedented. It matches a similar pattern observed in the high-rise image from October 2nd, when NASA's Mars Reconnaissance Orbiter photographed 3I Atlas at closest approach to Mars. That earlier image also showed an X-shaped glow around the nucleus, with material extending in directions perpendicular to the Sun-comet axis. At the time, the extensions were much smaller, only a few thousand kilometers across rather than a million. If both observations are capturing the same phenomenon, we are watching it evolve over time, watching the deployed objects drift further and further from their source. Dr. Loeb calculated what this would mean. If the breakup of 3I Atlas into multiple components started near Mars in early October, and the subcomponents have been drifting apart at 200 to 500 meters per second, ever since, we would expect to see exactly the kind of expanding X pattern that the observations reveal. The required velocity kick is remarkably similar to what chemical propulsion systems can achieve. It is far too large to be explained by solar tidal forces acting on fragments of a natural comet. Something active, something directed, would be required to produce these trajectories. The implications cascade outward. If 3I Atlas is deploying subcomponents, where are they going? The answer might be hidden in the geometry of the X pattern itself. The sideways extensions do not point randomly. They appear to trace specific angular trajectories relative to the main object's path. By analysing these angles and projecting forward, astronomers may be able to predict where the subcomponents will end up months or years from now. Some might be heading toward the inner solar system. Others might be aimed at Jupiter or the outer planets. If this interpretation is correct, 3I Atlas is not just passing through our cosmic neighbourhood. It is seeding it with smaller craft. There is a disturbing precedent for this kind of behaviour that has nothing to do with technology. Some comets are known to fragment as they approach the Sun. The thermal stress of solar heating can cause internal fissures to propagate, breaking a single nucleus into multiple pieces. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before its collision with Jupiter in 1994. More recently, Comet C 2025K1, confusingly also discovered by the Atlas survey system, has been observed breaking apart in the weeks following its own perihelion passage. But fragmentation of natural comets produces very different observational signatures. The fragments typically remain close together, drifting apart slowly due to subtle differences in their outgassing thrust and orbital parameters. They do not separate at hundreds of meters per second in geometrically precise patterns. They do not create narrow, collimated lines extending millions of kilometers from the main body. And critically, they do not maintain their coherence over weeks of observation. Natural fragments would be pushed and scattered by the solar wind. They would form diffuse clouds rather than straight lines. What we are seeing around 3I ATLAS looks more like controlled deployment than chaotic breakup. The timing also raises questions. If 3I ATLAS were a natural comet undergoing thermal stress fragmentation, we would expect the breakup to occur at or shortly after perihelion, when solar heating was most intense. The HIRIS observation from October 2nd, showing the initial X pattern, came nearly a month before perihelion. Whatever was happening, it started early. It started while 3I ATLAS was still approaching the Sun rather than retreating from it. This is not what we would expect from passive thermal fragmentation, but it is exactly what we would expect from a spacecraft executing a planned deployment sequence, spreading its probes while still in the optimal position to take advantage of solar gravity assists. There is another piece of this puzzle that deserves attention. 3I ATLAS has been observed rotating with a period of approximately 16 hours. Any material ejected from its surface should be flung outward by this rotation, creating a spiral or fan-shaped pattern as the object turns. The jets we observe should be smeared across many degrees of arc, tracing the rotation of the nucleus over the course of a single exposure. Yet the November 20th image shows jets that remain tightly collimated, extending in straight lines for millions of kilometers without visible spreading. The November 9th images showed similar collimation. The jets refuse to smear. This behavior is extraordinarily difficult to explain for a natural comet. If sublimating gas is being ejected from vents on the surface as the nucleus rotates, the resulting plumes should fan outward like water from a spinning sprinkler. We see nothing of the sort. Instead, we see what look almost like laser beams, narrow extensions that maintain their coherence across distances that should be impossible. One explanation would be that the jets are not coming from the rotating surface at all. They might be emerging from a stabilized source, something that maintains its orientation regardless of how the main body tumbles through space. A steered thruster, perhaps, a directed emission system, something that is not rigidly attached to the spinning nucleus. The astronomical community is divided on how to interpret these observations. Skeptics point out that image processing can introduce artifacts, that stacking multiple exposures can create spurious features, that what looks like a pattern might be coincidence viewed through the lens of confirmation bias. These are valid concerns. Science requires rigour, and extraordinary claims demand extraordinary evidence. But the pattern is now appearing in multiple independent observations. The high-rise image from Mars, the November 9th images from European observers, the November 20th stacked exposure, the November 22nd Puerto Rico photographs. Each shows geometric features that standard cometary models cannot explain. At some point, dismissing each observation as coincidence or artifact becomes less parsimonious than accepting that 3I ATLAS is doing something genuinely unprecedented. The next few weeks will be critical, as 3I ATLAS continues its outbound journey and approaches its closest point to Earth on December 19th. The opportunity for detailed observation improves. Ground-based telescopes with adaptive optics will be able to resolve finer details. Spectroscopic analysis may reveal the composition and velocity of whatever material is creating these sideways extensions. If the lines are satellite streaks, they will not appear in follow-up images taken at different times. If they are real features, they should persist and evolve as the deployed objects continue their drift away from the main body. And if they are real, if 3I ATLAS is genuinely releasing smaller objects into our solar system, then the question becomes not whether this is happening, but what those objects are for. Observers, probes, communication relays, resource collectors, the possibilities multiply as fast as our imaginations can generate them. We may not know the answer for years or decades, but we may be watching the first verifiable evidence that something from another star system has decided our little corner of the galaxy is worth investigating more closely. Where is the dust tail, the post-perihelion mystery that baffles scientists? Every comet that has ever passed close to the Sun has done the same thing. As solar radiation heats the frozen surface, ice is sublimate into gas. Dust particles embedded in that ice are liberated into space. The solar wind and radiation pressure push this material outward, away from the Sun, creating the magnificent tales that have inspired wonder and terror in human observers since the dawn of civilization. This is not a sometimes thing. This is not an occasional behaviour. This is what comets do. It is the defining characteristic that distinguishes comets from asteroids, the reason we call them dirty snowballs, the very phenomenon that gives comets their name, which derives from the Greek word for long-haired star. And yet 3I Atlas, after losing more than 13% of its total mass during its closest approach to the Sun, somehow failed to develop the dust tail that basic physics demands it should have. When 3I Atlas emerged from behind the Sun in early November of 2025, astronomers around the world turned their telescopes toward the pre-dawn sky with eager anticipation. The object had just completed its perihelion passage, coming within 203 million kilometres of our star. At that distance, solar irradiance would have delivered more than 33 gigawatts of power to its surface. That is roughly equivalent to 1/3 of the total nuclear power generation capacity of the entire United States, concentrated on an object perhaps 5 to 10 kilometres across. The heating should have been intense, the outgassing should have been dramatic, and the tail should have been spectacular. Instead, observers saw a fuzzy green ball with almost no visible tail at all. On November 5th, the Virtual Telescope project captured one of the first post-perihelion images of 3I Atlas. The object appeared as a compact glowing source against the background stars. There was a coma, certainly, that hazy envelope of gas and dust that surrounds any active comet. But where was the tail? Comet Lemon, a perfectly ordinary solar system comet photographed by the same telescope just 2 days earlier, displayed a clear, well-defined tail, streaming away from the Sun exactly as expected. 3I Atlas showed nothing comparable. Dr. Avi Loeb was among the first to recognise how strange this was. In his analysis, he worked backward from NASA's data on the object's non-gravitational acceleration. When a comet loses mass through outgassing, the expelled material creates a tiny but measurable thrust, like a rocket engine firing in slow motion. This thrust alters the comet's trajectory in ways that can be detected through precise orbital tracking. For 3I Atlas, NASA's Jet Propulsion Laboratory reported non-gravitational acceleration values that implied substantial mass loss. Loeb calculated that the object must have shed at least 13% of its total mass during the perihelion passage. Think about what that means. A comet 5 to 10 kilometres in diameter, weighing perhaps 33 billion tonnes according to recent estimates, lost at minimum 4 billion tonnes of material in a matter of weeks. 4 billion tonnes of ice, dust and gas liberated into space by the most intense solar heating of its entire journey through our cosmic neighbourhood. That material did not disappear. Conservation of mass is not optional. It went somewhere. And according to all our understanding of cometary physics, it should have formed a tail stretching hundreds of thousands or even millions of kilometres into space. For a typical comet, the scenario would proceed as follows. Dust particles freed from the sublimating ice are initially moving with the comet, but they quickly encounter solar radiation pressure, the gentle but persistent push of sunlight itself, which acts more strongly on small particles than large ones. This pressure decelerates the dust relative to the comet, causing it to fall behind. The solar wind adds its own push, especially on ionized gas particles. Over hours and days, this material spreads into the characteristic tail structure, with the larger dust grains curving gently away from the comet's trajectory and smaller particles and ions streaming directly away from the Sun in the gas tail. 3I Atlas has the coma. It has the gas emissions. The James Webb Space Telescope detected abundant carbon dioxide. Ground-based spectroscopy found nickel and other metallic elements. The object is clearly active, clearly losing material to space, but the expected dust tail is simply not there. The material being lost is not forming the structures that material should form. Several hypotheses have been proposed to explain this anomaly. The most conservative suggests that 3I Atlas might be unusually dust-poor. Perhaps it is composed primarily of volatile ices with very little rocky or dust-eat material embedded within. If there is no dust to be freed, there can be no dust tail. The high carbon dioxide to water ratio detected by Webb might support this interpretation. Carbon dioxide ice is lighter and more volatile than water ice, and a comet dominated by carbon dioxide might behave differently than the water ice dominated comets we are accustomed to studying. But this explanation has problems. The spectroscopic detection of nickel and other metals in the coma proves that 3I Atlas does contain non-volatile material. That nickel has to come from somewhere, and the somewhere is presumably dust or rocky material within the nucleus. The industrial nickel-to-iron ratio, which resembles manufactured alloys more than natural meteoritic abundances, suggests there is plenty of metallic content to form a dust tail, so why is that material not spreading into the expected structure? Another hypothesis involves particle size. Radiation pressure affects small particles much more strongly than large ones. If 3I Atlas is somehow releasing material primarily in the form of large grains rather than fine dust, those grains would be less affected by solar pressure and might remain closer to the nucleus rather than spreading into a visible tail. This could explain the compact appearance of the coma without requiring the object to be completely dust-free. But again, there are problems. We have spectroscopic evidence of gas emissions extending millions of kilometers from 3I Atlas. The gas is clearly being pushed by the solar wind into elongated structures. If dust were being released alongside this gas, it should be visible. The fact that we see gas tails but not dust tails suggests something is selectively affecting the dust in ways we do not understand. Dr. Loeb has proposed a more radical interpretation. What if the material being expelled from 3I Atlas is not dust at all, but rather exhaust from some form of propulsion system? Technological thrusters can be designed to minimize particulate emissions, expelling ionized gas at high velocity without the dusty byproducts of natural sublimation. The green color of the coma, consistent with ionized carbon compounds, would be compatible with certain types of propulsion chemistry. The lack of a dust tail might simply reflect the fact that there is no dust to form one because the mass loss is coming from engines rather than melting ice. This is speculative, certainly, but it is consistent with other anomalies we have discussed. The collimated jets that refuse to smear despite rotation, the forward anti-tail that advances ahead of the object, the precise trajectory alignment with Jupiter's hill radius. Each of these observations is difficult to explain for a natural comet. Together, they paint a picture of an object that is behaving in ways our models did not predict, because our models were not designed for this kind of object. The comparison with other comets is instructive. Comet C2025K1, discovered by the same Atlas survey system that found 3I Atlas, recently passed through perihelion and has been observed fragmenting in spectacular fashion. Images from November show this comet with a clear, dramatic tail and multiple fragments spreading apart in classic cometary fashion. This is what a natural comet does. This is what our models predict. 3I Atlas does none of it. Even more telling is the comparison with 2I Borisov, the previous interstellar comet detected in 2019. Borisov was smaller than 3I Atlas and approached the Sun less closely. Yet it developed a substantial tail that was easily visible in telescope images. It behaved, in other words, exactly like a natural comet should. Whatever makes 3I Atlas different, it is not simply the fact of being interstellar in origin. Borisov proved that interstellar comets can look and act just like their solar system cousins. 3I Atlas is departing from that template in ways that demand explanation. Some observers have pointed out that the ion tail of 3I Atlas has actually grown more prominent in recent weeks. Images from mid-November show a sharply defined gas tail extending behind the object, becoming more structured as time passes. Perhaps, the argument goes, we simply need to be patient. Perhaps the dust tail will develop as the object continues to cool and stabilize following the intense heating of perihelion. Natural variability in cometary behavior means we should not expect every object to follow an identical script. This is a reasonable point, and it may prove correct. The next few weeks will tell. If 3I Atlas develops a conventional dust tail as it approaches closest Earth encounter on December 19th, many of the anomalies will be explained away as premature interpretation of incomplete data. Patience and continued observation are the proper response. But there is something deeply strange about an object that loses 4 billion tons of mass without producing the visual signatures that mass loss should create. We are not talking about subtle differences from expectation. We are talking about a fundamental departure from the behaviour that defines what a comet is. If the dust is not forming a tail, either there is no dust, or the dust is not behaving like dust, or what we are calling dust is something else entirely. The December observations will be critical. As 3I ATLAS approaches Earth, we will have our best opportunity for detailed spectroscopic analysis of the coma composition. If the material is indeed ordinary cometary dust, there should be characteristic spectral signatures, silicon and iron and magnesium in the proportions found in primitive solar system material. If those signatures are absent, or if unexpected elements dominate, we will need to revise our assumptions about what 3I ATLAS is made of and where it came from. We may also be able to measure the size distribution of particles in the coma. This would tell us whether the missing tail is due to unusually large grains that resist solar pressure, or whether something else is going on. Every observation constrains the possibilities. Every data point narrows the range of viable hypotheses. Within weeks, we will know more. Until then, the missing tail remains one of the most puzzling aspects of an object that seems determined to defy our expectations at every turn. A comet without a proper tail is like a bird without wings. It challenges the very category we have placed it in, and it raises the uncomfortable possibility that perhaps we have been categorizing 3I ATLAS incorrectly from the very beginning. The James Webb's disturbing discovery, an 8-to-1 ratio, never seen before, when NASA's James Webb Space Telescope turned its powerful infrared gaze toward 3I ATLAS on August 6, 2025, scientists expected to learn something interesting about interstellar chemistry. What they discovered instead was something that challenges fundamental assumptions about where this object came from and how it formed. The data revealed a carbon dioxide to water ratio of approximately 8-to-1, among the highest ever recorded for any comet in history. To put that in perspective, typical solar system comets are dominated by water ice. Carbon dioxide is present, certainly, but as a secondary component, usually accounting for 5 to 15% of volatile emissions. 3I ATLAS has inverted this relationship completely. It is a carbon dioxide comet with a splash of water, not a water comet with a bit of carbon dioxide. And nobody can fully explain why. The observation came from Webb's near-infrared spectrograph, an instrument capable of dissecting light into its component wavelengths with extraordinary precision. By analysing which wavelengths are absorbed or emitted by the gas surrounding 3I ATLAS, researchers could identify the molecular species present in the coma and estimate their relative abundances. The signature of carbon dioxide was unmistakable, a strong spectral feature that dominated the data. Water vapour was present but strikingly subdued. When the researchers calculated the ratio, the result was startling enough that they checked their data multiple times before publishing. 8-to-1. For every molecule of water sublimating from the surface of 3I ATLAS, roughly 8 molecules of carbon dioxide are escaping into space. This is not a small deviation from normal. This is an entirely different chemical regime. To understand why this ratio is so significant, you need to think about how comets form. In the early solar system, the Sun was surrounded by a disk of gas and dust, the raw material from which planets and smaller bodies would eventually coalesce. Different volatile compounds freeze at different distances from the Sun, depending on their individual freezing points. Water ice, which is very stable, can exist relatively close to the Sun, inside what astronomers call the snow line. Carbon dioxide ice requires colder temperatures and can only survive further out. Carbon monoxide, which is even more volatile, freezes only at the most distant reaches of the protoplanetary disk. Comets that form near the snow line tend to be water-dominated because that is the volatile most abundant in their formation region. Comets that form further out contain more carbon dioxide and carbon monoxide. By measuring the relative abundances of these compounds, astronomers can essentially read a comet's birth certificate, determining roughly where in its parent disk it formed. For solar system comets, water dominance is the rule. Even comets from the distant Oort cloud, which formed in the coldest outer reaches of the protoplanetary disk, typically show water as their primary volatile. Carbon dioxide enrichment is observed occasionally, but an 8-to-1 ratio is essentially unheard of. Whatever planetary system 3I ATLAS formed in, it was a very different environment from our own. One possibility is that 3I ATLAS was born extremely far from its parent star. in a region so cold that carbon dioxide was the dominant solid while water remained locked in even colder forms, or simply was not abundant. This would imply a planetary system with unusual chemistry, perhaps one that formed from a molecular cloud with different elemental ratios than the cloud that birthed our Sun. Alternatively, the parent star might have been much cooler than the Sun, shifting all the ice lines inward and creating a planetary system dominated by exotic volatiles throughout. But there is another explanation, one that has gained considerable attention in recent weeks. The extraordinary carbon dioxide enrichment might not reflect the original composition of 3I Atlas at all. It might be a product of billions of years of cosmic ray bombardment during the object's journey through interstellar space. Galactic cosmic rays are high-energy particles, mostly protons and atomic nuclei, that permeate the galaxy. They are accelerated to near light speed by supernova explosions, neutron star mergers, and other cataclysmic events. When these particles strike the surface of an icy body, they trigger chemical reactions that can transform the molecular composition over time. Laboratory experiments have shown that cosmic ray irradiation of water ice produces a variety of oxidized compounds, including carbon dioxide and hydrogen peroxide. A research team from the Royal Belgian Institute for Space Aeronomy recently modelled what happens to an interstellar comet over billions of years of exposure to this cosmic ray environment. Their results, published just weeks ago, suggest that the outer layers of 3I Atlas have been so thoroughly irradiated that the surface chemistry no longer resembles the pristine material that originally formed around a distant star. The extreme carbon dioxide enrichment might be a radiation product, created by eons of cosmic ray bombardment converting water ice into more oxidized forms. The implications of this interpretation are profound. If the surface of 3I Atlas has been fundamentally transformed by radiation damage, then we are not observing the original interstellar composition. We are observing something created during the journey, a crust of irradiated material that tells us more about the interstellar medium than about the object's birth environment. The scientists described this as a paradigm shift for the study of interstellar objects. What we see is not what was sent. Dr. Roman Maggiolo, lead author of the radiation study, calculated that cosmic rays have altered the ice to a depth of 15 to 20 meters over the object's estimated 7 billion year lifespan. That is the entire observable surface layer. Everything we detect spectroscopically comes from this irradiated crust. The pristine interior, if it still exists, is hidden from view beneath layers of transformed material. This raises an obvious question. If the carbon dioxide enrichment is a radiation effect, should we not see similar ratios in all interstellar objects? 2I Borisov, the previous interstellar comet, was detected in 2019 and studied extensively. Its composition was unusual, but not as extreme as 3I Atlas. It showed elevated carbon monoxide levels, but a more typical water ice signature. Why would radiation processing affect these two objects so differently? The answer might lie in their ages. 3I Atlas is estimated to be approximately 7 billion years old, based on its trajectory through the galaxy. It comes from the thick disk of the Milky Way, an ancient population of stars that formed billions of years before our Sun. Borisov was younger, perhaps only a few billion years old, originating from the thin disk where stellar ages are more modest. The extra billions of years of exposure could account for the more extreme processing of 3I Atlas. But there is a problem with this explanation too. If cosmic ray irradiation produces carbon dioxide at the expense of water, the process should continue indefinitely. Given enough time, all water ice should be converted. Yet 3I Atlas still shows detectable water in its emissions. The ratio is extreme but not infinite. Some water remains. Either the irradiation process reaches a saturation point beyond which further conversion slows, or something else is going on that we do not understand. James Webb also detected carbon monoxide in the coma, though at lower abundances than carbon dioxide. This is interesting because carbon monoxide is even more volatile than carbon dioxide, sublimating at lower temperatures. Its presence confirms that 3I Atlas contains ices that formed under truly frigid conditions, much colder than the outer solar system. The combination of carbon dioxide dominance with carbon monoxide presence paints a picture of an object born in the deep freeze of interstellar space, or the outermost reaches of an unusually cold planetary system. The Webb observations also revealed something unexpected about the water emission. Despite its relative scarcity, water is being lost from 3I Atlas at a prodigious rate. Later observations suggested the object was venting water, quote, like a fire hose on full blast, losing hundreds of kilograms per second as it approached the sun. This seems paradoxical. If water is so scarce in the overall composition, how can it be escaping so rapidly? One possibility is that the surface layer of irradiated material acts as an insulating blanket, trapping heat and preventing it from penetrating to the water ice-rich interior. As 3I Atlas approached the sun and heated up, pockets of subsurface water ice began to sublimate violently, blasting through the irradiated crust in localized eruptions. The low abundance of water in the spectroscopic signature might reflect the small surface area of these eruption sites, rather than the overall water content of the nucleus. Deep beneath the carbon dioxide-rich surface, there might be substantial water ice waiting to be released. This interpretation has intriguing implications. If the water ice interior is separate from the carbon dioxide-rich crust, 3I Atlas might have a layered structure, an irradiated shell surrounding a more pristine core. Such a structure could have formed naturally through eons of radiation processing, or it could reflect intentional design, a protective outer layer shielding something more interesting within. The phrase intentional design might seem like a stretch, but consider the context. An object with a carbon dioxide-dominated crust would behave very differently from a water ice comet. Carbon dioxide sublimation begins at much greater distances from the sun, allowing the object to become active earlier in its approach. This early activity could serve as a kind of braking system, slowing the object through outgassing thrust before it reaches the inner solar system. Alternatively, the high reflectivity of carbon dioxide ice could help regulate surface temperature, preventing the interior from overheating during close solar approaches. If you were designing a spacecraft for interstellar travel, protecting it from cosmic ray damage would be a major engineering challenge. One solution would be to accumulate a thick layer of sacrificial material during the journey, material that absorbs radiation damage so the critical systems beneath remain functional. Carbon dioxide ice collected from the interstellar medium could serve this purpose perfectly. It is abundant in molecular clouds, it is chemically stable, and it creates a thick protective crust that regenerates over time as the craft passes through ice-rich regions of space. This is speculation, of course. The simplest explanation for the unusual carbon dioxide ratio is natural radiation processing of an unusually old interstellar comet. But the simplest explanation is not always the correct one. And given the cascade of other anomalies associated with 3I Atlas, keeping an open mind about alternative interpretations seems warranted. What is not speculation is that 3I Atlas is chemically unlike any object we have ever studied. Its 8:1 carbon dioxide to water ratio places it in a category of 1. Whatever made it, wherever it formed, it represents a fundamentally different kind of icy body than the comets we know from our own solar system. That alone makes it one of the most scientifically valuable objects to ever cross our path. That it happens to also display a dozen other anomalies only adds to the mystery we are trying to unravel. He's 7 billion years old, the irradiated traveller older than our sun. There is a number that dwarfs every human achievement, every civilization, every geological era in Earth's history combined. 7 billion years. That is the estimated age of 3I Atlas, making it not just the oldest comet ever observed, but one of the most ancient objects humanity has ever directly studied. To put this in perspective, our Sun formed approximately 4.6 billion years ago. The Earth coalesced from the protoplanetary disk about 100 million years after that. Life appeared on our planet roughly 3.8 billion years ago. The dinosaurs went extinct 66 million years ago. Anatomically, modern humans have existed for perhaps 300,000 years. Recorded civilization spans only about 5,000 years. 3I Atlas was already older than our Sun is today before our Sun even began to shine. The age estimate comes from an analysis of 3I Atlas's trajectory through the Milky Way galaxy. When astronomers traced the object's path backward through time, they discovered something remarkable. 3I Atlas does not come from the thin disk of the galaxy where our Sun and most familiar stars reside. It comes from the thick disk, an older, puffier component of the Milky Way that contains stars formed during a much earlier era of galactic history. the thick disk stars are typically 8 to 12 billion years old, formed when the universe itself was only a few billion years young. If 3I Atlas originated from a planetary system in the thick disk, it would naturally share that ancient provenance. The galactic trajectory analysis is not guesswork. It is based on precise measurements of the object's velocity and direction of approach. 3I Atlas entered our solar system, travelling at about 44 kilometers per second relative to the local standard of rest, the average motion of nearby stars. This is faster than both 1I Oumuamua and 2I Borisov, the previous interstellar visitors. More importantly, the direction of approach points back toward the thick disk population when projected through the galaxy's rotation. The object has been travelling through interstellar space for billions of years, accumulating cosmic ray damage with every passing eon, before finally encountering our Sun in 2025. What does it mean to be 7 billion years old? It means that 3I Atlas predates almost everything we know. When this object formed around its parent star, the Milky Way was a smaller, messier galaxy, still assembling itself through mergers with smaller dwarf galaxies. The chemical elements were less abundant. Heavy metals produced by supernova explosions had not yet enriched the galactic medium to present-day levels. The first generation of planetary systems was still being born, experimenting with configurations and compositions very different from what we see today. If 3I Atlas carries intact material from that era, it represents a time capsule from the ancient universe. The ices locked within its nucleus might preserve molecular species that no longer exist in the modern galaxy. The dust grains might record the conditions in a protoplanetary disk that formed when the universe was less than half its current age. This is why astronomers are so eager to study the object in detail. It is not just a comet, it is a messenger from deep time, carrying information that cannot be obtained any other way. But the age also poses challenges for interpretation. 7 billion years is an inconceivably long time for any object to survive. Consider what 3I Atlas has endured during its journey, passing through molecular clouds where gas and dust accumulate on surfaces, encountering cosmic ray particles that shatter molecular bonds and transform surface chemistry, experiencing tidal forces from passing stars that could perturb trajectories and stress internal structures, colliding with interstellar dust grains at velocities high enough to vaporize material on impact. The interstellar medium is not empty. It is a gauntlet of low-level hazards that accumulate over geological time. The research from the Royal Belgian Institute for Space Aeronomy explored one aspect of this long-duration exposure. By modelling cosmic ray flux over billions of years, the scientists calculated how deeply radiation damage would penetrate into an icy body. Their conclusion was sobering. The outer 15 to 20 metres of 3I Atlas have been so thoroughly processed by cosmic rays that the original molecular composition has been destroyed. What we observe spectroscopically is not the pristine material that formed 7 billion years ago. It is transformed matter, cooked by radiation into something new. This has implications for our interpretation of the unusual chemistry we discussed earlier. The extreme carbon dioxide to water ratio, the industrial nickel to iron ratio, the dominance of exotic volatiles. These might all be artifacts of radiation processing rather than reflections of original composition. We are seeing what billions of years of cosmic ray exposure creates, not what the parent planetary system contributed. The true nature of 3I Atlas is hidden beneath layers of transformed material that we cannot see through. But here is where things get interesting. If natural objects are so thoroughly transformed by interstellar travel that their original nature is unrecoverable, how would we ever distinguish a natural ancient comet from something else? If 3I Atlas were a technological artifact launched 7 billion years ago, it too would have accumulated a thick crust of irradiated material during its journey. It too would show unusual chemistry dominated by radiation products. It too would appear, on the surface, to be exactly what we would expect from an ancient natural object. The camouflage would be perfect, not by design necessarily, but by the physics of interstellar travel. Any object crossing the galaxy for billions of years will end up looking like a radiation-processed icy body, regardless of what it started as. The interstellar medium does not care whether it is coating a frozen rock or a dormant spacecraft. It transforms the surface either way. This is a humbling thought. It suggests that we might never be able to determine the true nature of 3I Atlas through surface observations alone. the information is lost, overwritten by cosmic ray damage like a hard drive that has been degaussed. Only by penetrating beneath the irradiated crust, only by reaching the pristine interior could we potentially learn what this object actually is, and we have no spacecraft capable of that kind of investigation. The age of 3I Atlas also raises questions about what has happened to its source system over the intervening billions of years. Stars like the Sun have lifespans of roughly 10 billion years before exhausting their hydrogen fuel and expanding into red giants. A star that formed 7 billion years ago, if it were similar to the Sun, would now be approaching the end of its main sequence life. Its planetary system would be in flux, with inner planets potentially engulfed by the expanding stellar atmosphere and outer planets perturbed by mass loss from the dying star. The civilization that might have existed there, if one ever did, would be long gone, destroyed, or fled to safer harbours elsewhere in the galaxy. This timeline creates an interesting scenario for speculation. If 3I Atlas is a probe launched by an intelligent civilization, that civilization would have needed to exist around a thick disk star roughly 7 billion years ago. That is an extraordinary claim, implying intelligence arising when the universe was less than half its current age, when heavy elements were scarcer and stable. Planetary systems might have been rarer. But the universe is vast, and 7 billion years provides enormous time depth. Even if technological civilizations are exceedingly rare, the sheer number of stars in the early thick disk means some could have arisen. Such a civilization would be unimaginably ancient by human standards. It would have risen and fallen while our galaxy was still taking shape. Its artifacts, if any survived, would be the oldest technological objects in existence. They would predate every other intelligence that has since emerged. They would be, in a very real sense, the elder things of the cosmos, remnants of minds that contemplated the universe before the sun was born. This is pure speculation, of course. The scientific evidence points toward 3I Atlas being a natural interstellar comet, albeit an unusual one. The extraordinary claims require extraordinary evidence, and we do not yet have that evidence. But the age of the object opens doors to possibilities that younger objects would not permit. A comet ejected from a planetary system a few million years ago could not plausibly be artificial, because there is no reason to think intelligence existed in our cosmic neighbourhood that recently. A comet 7 billion years old exists in a time frame where almost anything becomes possible. What we can say with confidence is that 3I Atlas represents our only direct sample of material from the ancient thick disk population. Everything else we study, every meteorite, every asteroid, every comet from the Oort cloud, originated in our own solar system less than 5 billion years ago. 3I Atlas comes from elsewhere and elsewhen, a genuine alien in the most literal sense, even if it is nothing more than a frozen ball of irradiated ice. It is a frozen ball of irradiated ice that has travelled further and longer than any object we have ever examined. The privilege of studying such an object is immense. Future generations of scientists may never have another opportunity like this. Interstellar visitors arrive in our solar system only once every few decades, and most are too small or too fast to study in detail. 3I Atlas is large, bright, and taking its time as it loops through the inner solar system. The window for observation will remain open for months, allowing detailed characterization that was impossible for 1I Oumuamua, which was discovered only as it was already departing. We must make the most of this opportunity. Every spectrum, every image, every data point constrains what 3I Atlas is and where it came from. In 20 years, we will look back on this moment and evaluate how well we used our brief encounter with an object 7 billion years in the making. The universe has sent us a messenger from deep time. The least we can do is listen carefully to what it has to say. A December 19th, closest approach, what the next 25 days could reveal. In exactly 25 days from now, something extraordinary will happen. 3I Atlas will reach its closest point to Earth, passing within 269 million kilometres of our planet, approximately 1.8 times the distance from Earth to the Sun. This is still remarkably far by human standards, far enough that the object poses absolutely no threat to our world, but close enough that our most powerful telescopes will have their best opportunity to study this interstellar visitor in unprecedented detail. What happens during that observation window could confirm or overturn everything we think we know about 3I Atlas. The next 25 days may be the most consequential period in the history of interstellar object research. The The December 19th approach marks a turning point in the investigation. Until now, observations of 3I ATLAS have been constrained by geometry and timing. When the object was discovered in July, it was still far from the Sun, its activity muted and its features difficult to resolve. As it approached perihelion in October, it moved behind the Sun from Earth's perspective, becoming unobservable to ground-based telescopes for several critical weeks. The post-perihelion images have been illuminating, but limited by the object's distance and position in the pre-dawn sky, where atmospheric turbulence degrades image quality. December 19th changes all of that. 3I ATLAS will be high in the sky during the best observing hours. It will be bright enough for detailed spectroscopic analysis, and most importantly, it will be close enough that features spanning thousands of kilometres can be resolved by adaptive optics systems on the world's largest telescopes. The Keck Observatory in Hawaii, the Very Large Telescope in Chile, the Gemini telescopes in both hemispheres, all of these facilities will be pointed at 3I ATLAS during its close approach. The data flood that results could answer questions that have tantalised researchers for months. The first priority will be spectroscopic analysis of the jets. As we discussed earlier, 3I ATLAS displays peculiar jet structures that have refused to behave like normal cometary outgassing. They remain collimated despite the object's rotation. They extend perpendicular to the Sun-comet axis, where no natural force should push them. They have persisted for months with little apparent change in orientation. Understanding what these jets actually are requires measuring two things: their composition and their velocity. Composition tells us what material the jets are made of. If they show the spectral signatures of water vapour, carbon dioxide and carbon monoxide in the proportions expected from sublimating ice, that would support the natural comet hypothesis. If they contain unexpected elements, particularly metals or compounds not associated with cometary activity, that would raise serious questions about the object's nature. The industrial nickel-to-iron ratio already detected in the coma is intriguing but not definitive. More detailed spectroscopy could reveal whether this ratio is consistent throughout the jets or concentrated in specific structures. Velocity is even more diagnostic. When ice sublimates from a comet's surface, the resulting gas can only travel so fast. The thermal energy available from solar heating limits the exhaust velocity to a few hundred meters per second at most. This is a hard physical constraint that applies to all natural comets, regardless of size or composition. If the jets of 3I ATLAS are moving at thermal velocities, they are almost certainly natural. But if they show velocities of several kilometers per second or more, that would be difficult or impossible to explain through passive sublimation. High-velocity jets would require an active propulsion mechanism, something pushing the material harder than sunlight ever could. The December observations should be able to measure jet velocities through Doppler spectroscopy. By analysing the slight shifts in spectral lines caused by material moving toward or away from the observer, astronomers can determine how fast the jets are travelling. This technique has been used successfully on many solar system comets. Applying it to 3I ATLAS during close approach could provide definitive evidence about the nature of its unusual emissions. Beyond spectroscopy, the close approach will enable high-resolution imaging that could resolve surface features on the nucleus itself. Current estimates place the diameter of 3I ATLAS somewhere between 5 and 10 kilometers, possibly larger. At closest approach, adaptive optics systems on 8 to 10 meter class telescopes might achieve resolution of a few dozen kilometers, enough to detect any gross asymmetries or structures on the nucleus. If 3I ATLAS has appendages, antennae, solar panels, or other geometric features inconsistent with a natural icy body, this would be the best opportunity to detect them. More realistically, imaging could reveal the detailed structure of the coma and jets in ways that current observations cannot match. The X-shaped pattern seen in the November 20th images was barely resolved, its interpretation uncertain. At closer range and with higher resolution, the same features would be much clearer. If smaller objects are indeed being deployed from 3I ATLAS, they might become individually detectable as distinct points of light separating from the main body. The geometric relationships between the nucleus, the jets, and any subcomponents would constrain theories about what is happening and why. The timing of the close approach is also scientifically significant. December 19th comes approximately 50 days after perihelion, enough time for any post-perihelion changes to have developed fully. If 3I ATLAS was going to fragment under thermal stress, it would likely have done so by now. If it was going to develop a conventional dust tail, that should be visible. If its trajectory was going to deviate from predictions due to outgassing thrust, the deviations would be measurable. Whatever state the object is in on December 19th represents its stable post-perihelion configuration, the form it will maintain as it journeys outward toward Jupiter and eventually beyond the solar system. There is another aspect of the close approach that deserves attention. December 19th is the point where 3I ATLAS transitions from approaching Earth to receding from it. After that date, every day increases the distance between us and the interstellar visitor. The window of opportunity begins to close. While observations will certainly continue into 2026, each passing week will see the object fade and shrink in our telescopes. The detailed characterization possible in late December will become progressively more difficult. This creates urgency. The astronomical community has one best chance to answer the foundational questions about 3I ATLAS. Is it a natural comet displaying unprecedented behavior, or is it something else entirely? The data collected over the next few weeks will be analyzed and debated for years. It may be decades before another interstellar object this large and bright passes through our solar system. We must make every observation count. Some researchers are already preparing for the possibility that the close approach observations will deepen, rather than resolve the mystery. If the jet velocities are ambiguous, neither clearly thermal nor clearly propulsive, interpretation will remain contested. If the surface features are too small to resolve even at closest approach, the nucleus will remain an enigma. If the chemical composition shows unusual elements but not definitive technological signatures, both natural and artificial explanations will remain viable. Science proceeds through accumulated evidence, not single decisive experiments. 3I ATLAS may refuse to reveal its nature no matter how carefully we look. But there is also the possibility of a breakthrough. Imagine if the spectroscopy shows jets moving at 10 kilometers per second, far beyond what sublimation can produce. Imagine if high-resolution imaging reveals geometric structures inconsistent with natural formation. Imagine if multiple independent observations converge on the same extraordinary conclusion. The history of astronomy includes moments of sudden revelation, when data transforms from ambiguous to decisive in a single observation. The December 19th close approach could be such a moment. The broader public has begun to take notice. Media coverage of 3I ATLAS has intensified in recent weeks, with headlines alternating between sober scientific reporting and breathless speculation about alien spacecraft. NASA's November 19th press conference attempted to calm the speculation with definitive pronouncements about the object's cometary nature, but the pronouncements have not quelled interest. If anything, the agency's confident assertions have fueled skepticism among those who note the anomalies that official statements fail to address. December the 19th will be a moment of public as well as scientific reckoning. If the observations confirm that 3I ATLAS is merely an unusual comet, interest will likely fade. The object will become a footnote in astronomical history, studied by specialists but largely forgotten by the general public. But if the observations raise more questions than they answer, if the anomalies persist and deepen, the story of 3I ATLAS will only be beginning. Public fascination with potential extraterrestrial activity shows no signs of diminishing. An interstellar object that defies explanation would capture imagination worldwide. For now, we wait. The telescopes are being prepared. The observation proposals have been submitted and approved. The data pipelines are ready to process whatever 3I ATLAS reveals. In 25 days, the interstellar visitor will be as close as it will ever come to our world. Whatever happens then, humanity will have looked more carefully at a messenger from another star system than at any object in history. The universe has given us this opportunity. What we learn from it depends on how carefully we are willing to look. The night of December 19th will find astronomers at observatories around the world pointed at the same small patch of sky. In Chile and Hawaii, in Spain and Australia, in every location with major telescope facilities, the same object will be the centre of attention. For a few hours, 3I ATLAS will unite the global astronomical community in shared wonder and shared uncertainty. Whatever it is, wherever it came from, the object from another star will have our full attention, and perhaps, if we are very lucky, it will finally begin to give up its secrets. The industrial nickel signatures and the chemical fingerprint of manufacturing. Deep in the spectroscopic data from 3I ATLAS lies a chemical signature that has quietly troubled researchers since it was first detected. The object's gas emissions contain far more nickel than iron, a ratio that is extremely unusual for any natural celestial body, and remarkably similar to what we find in industrially produced nickel alloys. This is not the kind of anomaly that grabs headlines or sparks viral speculation. It is subtle, technical, buried in the details of elemental abundance measurements. But for those who understand what it implies, the nickel signature may be the most disturbing finding yet about the true nature of 3I ATLAS. To appreciate why this matters, you need to understand something about the cosmic abundance of elements. In the universe at large, iron is one of the most common metals. It is the end product of stellar nucleosynthesis, the most stable nucleus in terms of binding energy per nucleon. When massive stars die in supernova explosions, they seed the galaxy with iron. Every rocky planet, every asteroid, every comet nucleus contains iron in roughly predictable proportions. Nickel is also produced in supernovae, but in smaller quantities. The cosmic ratio of iron to nickel is approximately 18:1. This ratio appears consistently in meteorites, in cometary dust, in the atmospheres of stars. It is one of the most robust patterns in cosmochemistry. Natural objects in our solar system respect this ratio. When astronomers analyze the spectra of comets, they find nickel and iron in the expected proportions. The materials that make up these objects formed from the same interstellar medium that formed the Sun and planets, and they inherited the cosmic abundance pattern. Variations occur, certainly, but within a relatively narrow range. A natural comet might show an iron to nickel ratio of 15:1 or 20:1, but the iron always dominates. 3I ATLAS breaks this pattern completely. Spectroscopic observations from the Very Large Telescope and other facilities have detected nickel emissions that are orders of magnitude stronger than expected relative to iron. The exact ratio is still being refined, but preliminary estimates suggest nickel either equals or exceeds iron in the object's emissions. This is not a small deviation from normal. This is a fundamental departure from cosmic chemistry. There are very few natural processes that can enrich nickel relative to iron. Certain types of supernova, particularly those involving white dwarf stars in binary systems, produce elevated nickel abundances. But these explosions are rare, and the materials they produce are rapidly mixed into the general interstellar medium. The chance that 3I ATLAS formed exclusively from nickel-enriched supernova debris, avoiding the iron-rich material that dominates galactic chemistry, is vanishingly small. What does produce nickel-enriched materials reliably and consistently is industrial processing. Nickel alloys, particularly those designed for high temperature and high stress applications, are carefully engineered to contain more nickel than would occur naturally. Inconel, a family of nickel-chromium superalloys used in aerospace applications, contains 60 to 70% nickel. Manel, used in marine and chemical processing environments, is about 2/3 nickel. Nichrome, used in heating elements, is typically 80% nickel. These alloys are prized precisely because their composition differs from natural materials, giving them properties that pure metals or cosmic abundance mixtures cannot match. When Dr. Avi Loeb first highlighted the nickel anomaly, he framed it carefully. The nickel-to-iron ratio in 3I ATLAS, he noted, resembles industrially produced nickel alloys more than any natural astronomical object. This is not proof of artificial origin. There might be natural processes we do not yet understand that could produce similar enrichment. But it is a data point that fits more comfortably with the artificial hypothesis than with the natural one. There is another chemical anomaly that compounds the mystery. Observations have also revealed an unusual nickel-to-cyanide ratio in the emissions of 3I ATLAS. In typical comets, cyanide compounds are common products of photodissociation when ultraviolet light breaks apart larger molecules in the coma. The ratio of nickel to cyanide in solar system comets follows a fairly consistent pattern. In 3I ATLAS, that ratio is orders of magnitude higher. There is far more nickel relative to cyanide than in any of the thousands of comets we have studied, including 2I Borisov, the previous interstellar visitor. How do we explain this? One possibility is that 3I ATLAS simply formed in an environment with unusual chemistry. Perhaps its parent planetary system was enriched in nickel-producing elements through some quirk of stellar evolution or local supernova contamination. Perhaps the formation process concentrated nickel-bearing dust grains in ways that do not occur in our solar system. These explanations are not impossible, but they require invoking processes we have never directly observed. Another possibility connects to the missing dust tail we discussed earlier. If 3I ATLAS is not releasing significant amounts of dust, the traditional source of metallic emissions in cometary spectra, where is the nickel coming from? One explanation would be direct outgassing of nickel-bearing compounds from the nucleus itself. Nickel carbonyl, a compound of nickel and carbon monoxide, is volatile enough to sublimate at the temperatures 3I ATLAS experiences near perihelion. Intriguingly, nickel carbonyl is used industrially in the Mond process for refining nickel. It is not a compound that forms naturally in significant quantities. The detection of nickel carbonyl in the emissions of 3I ATLAS would be a remarkable finding. It would suggest either that the object formed in an environment where this compound was abundant, which seems unlikely given its reactivity and short lifetime in space, or that some process within 3I ATLAS is actively producing nickel carbonyl as a byproduct. Industrial manufacturing using nickel-containing materials would naturally produce nickel carbonyl as waste. If 3I ATLAS were processing raw materials gathered during its journey, refining metals for structural repair or other purposes, nickel carbonyl emissions would be expected. This interpretation connects to another hypothesis we have discussed. The forward-advancing anti-tail might not just be protective or exploratory. It might be a collection system, gathering metallic dust and debris from the object's path and funneling it toward the nucleus for processing. The unusually high nickel emissions could represent the waste stream from this processing, the byproduct of taking in raw interstellar material and extracting useful components, in situ resource utilization at interstellar scales. Dr. Loeb has explicitly raised this possibility. In his analysis of the forward anti-tail, he suggested that 3I ATLAS might be deploying nanomachines ahead of its trajectory to collect metallic fragments. These fragments would be cannibalized for use inside the vessel, perhaps to repair damage from micrometeorite impacts or to manufacture new components. The nickel emissions would be the signature of this activity, the smoke from a factory hidden inside what we are calling a comet. This is speculative, certainly, but it is the kind of speculation that the data invites. When an object shows chemical signatures that resemble manufactured alloys more than natural materials, when the ratios defy cosmic abundance patterns in ways that industrial processing would produce, when the emissions include compounds used in metallurgical refining, the artificial hypothesis becomes increasingly difficult to dismiss. Critics would point out that we have studied only a handful of interstellar objects. Our sample size is 3, and only 2 of those, 2I Borisov and 3I ATLAS, were observed closely enough to characterize chemically. Perhaps interstellar objects routinely show unusual compositions because they form in environments very different from our solar system. Perhaps the cosmic abundance ratios we consider normal are actually provincial, reflecting local conditions rather than universal laws. Perhaps 3I ATLAS is the first truly representative sample of what is out there, and our solar system comets are the anomalies. These are valid points. Science requires humility about the limits of our knowledge, but they do not explain why 3I ATLAS's chemistry specifically resembles industrial alloy compositions rather than some random alternative pattern. If the enrichment were in some other element, if the ratios pointed nowhere in particular, the coincidence argument would be more compelling. The fact that the enrichment is in nickel, and specifically in proportions that match manufactured materials, is at minimum a remarkable coincidence. The December close approach observations should help resolve this question. More detailed spectroscopy will refine the abundance measurements and potentially detect additional metallic species. If the nickel enrichment is consistent throughout the coma, it likely reflects the bulk composition of the nucleus. If it is concentrated in specific jets or regions, it might indicate localized processes, possibly including the processing activity we have speculated about. Either way, more data will constrain the interpretations. We should also consider what the absence of certain elements might tell us. Industrial alloys are carefully designed to exclude impurities that would degrade their properties. If 3I ATLAS shows not just nickel enrichment, but also unusual depletion in elements that contaminate metallurgical processes, that would strengthen the manufacturing hypothesis. The pattern would be too specific, too purposeful to dismiss as coincidental. For now, the nickel signature remains one data point among many. It fits into a mosaic of anomalies that individually might be explained away, but collectively point towards something unprecedented. The forward anti-tail, the missing dust tail, the trajectory precision, the X-shaped jet pattern, the chemical composition. Each piece adds to a picture that becomes harder to reconcile with a simple, frozen ball of interstellar ice. What 3I Atlas actually is remains unknown. But what it is made of is increasingly well characterized, and the chemistry alone is enough to make any careful scientist pause. Something about this object is different at the atomic level. The elements do not add up the way cosmic chemistry says they should. Whether that difference reflects exotic natural origins or something more deliberately constructed is the question that future observations must answer. A March 16th, 2026, the Jupiter encounter. We cannot afford to miss everything we have discussed. Every anomaly, every mystery, every tantalizing hint about the true nature of 3I Atlas leads inevitably to a single date, March 16th, 2026. On that day, approximately 4 months from now, the interstellar visitor will reach its closest approach to Jupiter, passing within 53.4 million kilometers of the largest planet in our solar system. That distance is not random. As we explored earlier, it matches Jupiter's hill radius with precision that defies statistical probability. If 3I Atlas has any purpose beyond simply drifting through the cosmos, if it intends to leave anything behind in our solar system, the Jupiter encounter is when and where it will happen. The significance of this encounter cannot be overstated. Jupiter represents the gravitational anchor of the outer solar system. Its massive influence shapes the orbits of asteroids, captures stray comets, and perturbs anything that passes too close. For billions of years, Jupiter has acted as both shield and vacuum cleaner, absorbing impacts that might otherwise threaten the inner planets. Any civilization observing our solar system from across the galaxy would recognize Jupiter as the dominant feature beyond the Sun itself. If you wanted to establish a presence in our cosmic neighborhood, Jupiter would be the logical place to start. The hill radius, where 3I Atlas will pass, is particularly strategic. Inside this boundary, Jupiter's gravity exceeds the Sun's gravitational pull. Objects can be captured into stable orbits without the Sun pulling them away. The Lagrange points L1 and L2, located at the hill radius, offer positions where gravitational forces balance perfectly. Spacecraft parked at these points require minimal fuel for station keeping. They can observe the Jupiter system indefinitely. They can maintain their position for centuries, millennia, longer. NASA's Juno spacecraft currently orbits Jupiter and will still be operational during the 3I Atlas encounter. Originally scheduled to end its mission in September of 2025, with a controlled deorbit into Jupiter's atmosphere, Juno received a mission extension that keeps it alive through at least the encounter date. This is fortuitous. Juno carries instruments capable of detecting objects and emissions that ground-based telescopes might miss. Its ultraviolet spectrograph could detect unusual gas compositions. Its magnetometer could sense electromagnetic disturbances. Its particle detectors could register debris or exhaust products. If 3I Atlas does anything unusual during its Jupiter passage, Juno might be our best witness. Proposals have circulated within the astronomical community to actively redirect Juno toward 3I Atlas. A study by Dr. Loeb and colleagues calculated that with sufficient remaining fuel, Juno could theoretically intercept the interstellar object, passing within tens of millions of kilometers, rather than merely observing from Jupiter orbit. This would require trajectory maneuvers that NASA has not approved, and the fuel situation is uncertain, but the possibility exists. For the first time in history, we might have a spacecraft capable of closely encountering an interstellar visitor. Even without an intercept, Juno's observations will be valuable. The spacecraft's remote sensing instruments can characterize 3I Atlas from a perspective unavailable to Earth observers. While we see the object illuminated primarily from our vantage point, Juno can observe at different phase angles, potentially revealing surface features or emission patterns hidden from terrestrial telescopes. The combination of Earth-based and Jupiter-based observations will provide three-dimensional context that neither alone can offer. ESA's JUICE spacecraft, currently en route to Jupiter, will also be in position to observe. Though JUICE will not arrive at Jupiter until 2031, it will pass within approximately 64 million kilometers of 3I ATLAS during the March 2026 encounter. Its instruments, including ultraviolet and infrared spectrometers, could capture data on the interstellar object as a secondary science target. The more eyes we have on 3I ATLAS, the better our chances of detecting anything unusual. What might we see during the Jupiter encounter? If 3I ATLAS is a purely natural object, we would expect its behaviour to remain consistent with what we have observed so far. Continued outgassing producing the unusual jets, gradual fading as it moves further from the Sun, and solar heating diminishes. Perhaps development of a more conventional tail as conditions change. The object would simply coast past Jupiter, barely influenced by the planet's gravity at the edge of the Hill sphere, and continue its journey out of the solar system. But if the artificial hypothesis has any merit, the Jupiter encounter is when we might expect to see activity. The release of probes or satellites that could become captured in Jupiter's gravitational influence, a trajectory manoeuvre to fine-tune the approach, or deposit payloads at specific locations. Electromagnetic emissions as communication systems activate or dormant systems power up. Any of these would represent definitive evidence that we are dealing with something more than a cosmic icy body. Dr. Loeb has emphasized this point repeatedly in recent weeks. If new objects appear in Jupiter's orbital environment after 3I ATLAS passes, objects that we did not put there and cannot explain through natural processes, the implications would be profound. We would have direct evidence of extraterrestrial technology operating in our solar system, not ambiguous signals from distant stars, not statistical anomalies in chemical ratios, actual physical objects in Jupiter orbit that require artificial explanation. The detection of such objects would be challenging but not impossible. Juno's instruments could potentially register new radar signatures or particle trails. Ground-based telescopes could search for points of light that were not present before the encounter. Over the following months and years, as any deployed objects settled into stable orbits, they would become easier to locate and characterize. The search would be intensive, driven by the stakes involved. Of course, absence of evidence would not constitute evidence of absence. If 3I ATLAS passes Jupiter without any detectable activity, that could mean it is natural. Or it could mean that its technology operates below our detection thresholds, or that its mission does not involve Jupiter at all, despite the suspicious trajectory precision. The universe is under no obligation to provide clear answers to our questions. What seems certain is that March 16th will mark the beginning of the end of our close encounter with 3I ATLAS. After Jupiter, the object will continue accelerating outward, its velocity carrying it beyond the reach of even our most ambitious spacecraft. Within a few years it will fade from visibility entirely, lost in the vast darkness between stars. Whatever secrets it carries will go with it, preserved in that irradiated crust for another billion years, until it reaches its next destination if it has one. This is why the next 4 months matter so much. Every observation we make now, every data point we collect, every anomaly we document, becomes part of the permanent record of humanity's third encounter with an interstellar object. Future generations will study what we learned about 3I ATLAS long after the object itself has vanished from our instruments. The quality of their understanding depends on the quality of our investigation, and so we watch. We point our telescopes at this visitor from deep time. We analyze its light for clues about composition and structure. We track its trajectory with exquisite precision, looking for deviations that might reveal hidden intent. We speculate and theorize and debate, because that is what scientists do when confronted with something unprecedented. 3I ATLAS has given us more questions than answers. Perhaps that is the point. Perhaps the questions themselves are the gift. As this video draws to a close, I want to thank you for joining me on this journey through one of the most remarkable astronomical events of our lifetime. Whether 3I ATLAS is a natural comet from a distant star system or something more deliberately constructed, it represents our best window yet into the interstellar medium and the objects that travel through it. The anomalies we have discussed, the forward anti-tail, the missing dust tail, the trajectory precision, the industrial chemistry, the ancient age, the mysterious jets, these are not sensationalism. They are real scientific observations that demand explanation. In the coming weeks and months, as 3I ATLAS reaches closest Earth approach and then continues toward Jupiter, we will learn more. Perhaps the mysteries will resolve into mundane explanations, leaving us with an unusual but natural interstellar comet to add to our catalogues. Perhaps the mysteries will deepen, pointing toward conclusions that challenge our assumptions about life, intelligence, and our place in the universe. Either outcome advances human knowledge, either outcome is worth pursuing with rigour and humility. If you found this exploration valuable, please consider liking this video and subscribing to the channel. Your support allows me to continue creating content about the wonders of the cosmos and the mysteries that still await explanation. Share your thoughts in the comments. Tell me whether you believe 3i Atlas is natural or artificial. Tell me what evidence would change your mind. The conversation about this object is just beginning, and every perspective adds value. As always, remember that the universe is vast beyond comprehension, and ancient beyond imagination. We are newcomers here, our entire civilization a brief flicker in cosmic time. Objects like 3i Atlas remind us how much we have yet to learn, and how much lies waiting to be discovered. Keep looking up, keep asking questions, keep wondering about what else might be out there, travelling between the stars on journeys we can barely imagine. Thank you for watching. Good night, and may your dreams be filled with starlight.